So this is chapter 14, I think. Wait, am I on the wrong screen? Wait. Hold up. Oh, no, I'm on the right screen. I'm good. Okay, chapter 14. So we'll be learning about different types of solids. And the main concept of this chapter is the crystal lattice. So a crystal lattice is the three-dimensional arrangement of particles in any solid, in a crystalline solid. So there's two types of solids. There's crystalline solids and there's amorphous solids. Now, amorphous sounds like, is the definition that sounds just like the word. That's the connotation of the word is kind of the definition. Amorphous, meaning it's not morphous. It's the opposite of morphous. So it's just like a bunch of glob put together. It's just like there's no order to it. If you have a lot of metals are going to be like that, just a bunch of the atoms put together. A lot of different alloys are like that, where you just have them next to each other. There's no three-dimensional arrangement that can be repeated over a course of space. Like a crystal lattice has a three-dimensional arrangement that repeats itself. And it repeats itself in the form of the unit cell, which is the smallest unit of the crystal lattice. And there's different types of unit cells, and you can box them different ways. Now, you can say there's lattice points, lattice planes, whatever, but we're going to look at them in three-dimensional units. And we'll just go right to it. Before we get to defining all of them, we want to talk about how it can be discovered what the crystal structure is of a solid, because we don't know, we can't tell from looking at it if it has a body-centered cubic, face-centered cubic, and simple cubic. Those are the three different types of unit cells, but we can't determine that from looking at it or even from knowing what element it is. We have to use X-ray diffraction, which uses light and which bounces off the crystals and forms a diffraction pattern. And from this diffraction pattern, we can tell the three-dimensional structure and the arrangement of them. So the technique, crystal is struck by a beam of X-rays and they're reflected. The wavelength is adjusted to result in an interference pattern, meaning the amplitudes will coincide with each other, and at which point the wavelength is an integral multiple of the distances between the particles. Don't go too crazy with it. There is an equation which we'll get to, and it will be given to you. But basically, here's how it occurs. You have a source of X-rays. The X-rays will go through the hole, and it'll be a beam. A beam hits the solid, and they will diffract in a certain pattern. This pattern and the angle at which they diffract can give you an image, a crystallography image, which can then tell you where the atoms are and their three-dimensional arrangement. So this, if you can imagine, if you flip this three-dimensional structure facing your screen, facing you, it'll kind of look like this. That's where they get that from. And there's different ways to interpret it. And the equation that goes along with this is called Bracks Law. So you can tell a lot from Bracks Law. You can tell the distance between two different layers. So these crystals, think about it as a lot of different layers of crystals, or like honeycombs, right? Picture like honeycombs, but layers of honeycombs stacked on top of each other. That's exactly what this is. And the angle of diffraction or reflection can tell you the distance between these kind of honeycomb layers, which can give you, if it's a larger distance, then you have a larger angle kind of thing. And you have a larger wavelength too, according to the equation. So over variables, we can look at D. So D is the distance between the two layers of the particles. N is the energy level. And then, yes. And then, well, no, N's an integer. It could be, usually it's 1. And then lambda is your wavelength. And then A is your distance between the two paths, which they'll give to you. They'll give that to you. And then you have sine theta. Theta is the angle of diffraction. So if we were to solve for a question involving Braggs law, here's what one would be. So an X-ray beam with the wavelength of 154 picometers. That's picometers. So this is a very small wavelength, very high frequency. It's going to be a very intense radiation. And it makes sense. It's an X-ray. So your picometers would be 154 times 10 to the negative 12. is striking an iron crystal resulting in the angular reflection of 32.6. Assuming n equals 1, calculate the distance between the layers. So we can straight up use Braggs Law. So n, good question. N is always 1, unless they tell you otherwise. So n, usually it's going to be 1. They will always assume it's 1, unless they tell you otherwise. So just go with 1, yes. Okay, so then you use our Braggs Law, D equals n times lambda over 2 sine theta. And now you can plug in our value. So you have n equals 1. Lambda is 154 picometers, but you don't have to, you can change it to meters, but you don't have to. And the reason why is because there's no constant that has meters in it. So before, when we were dealing with wavelengths, we always had to convert it to meters. Why is it different now? Or why didn't we always have to convert? Why did we always have to convert to meters back then when we were dealing with wavelength and frequency? Anybody know? Why did we do it back then? Why did we have to change to meters? Lewis, good job. Speed of light. Because we had the speed of light constant in there. It's 3 times 10 to the 8th meters per second. So we had a constant that had meters in it. In this case, we're just using the distance to figure out another distance. And they can be, and there's no constant involved. So we can convert it, or we can keep it as picometers. And then you can just plug in the angle, and you can get your answer. So, yeah. Does this make sense? So the distance between the layers should be on the scale of the atomic radius. It should be around the atomic radius because it's from nucleus to the next atom. So it could be, it should be, because most of them are touching each other. All right, so the cubic unit cell. So with these unit cells, we're going to see a bunch of different arrangements three-dimensionally. And here's one of them. Here's the simple cubic. We'll start with this. We'll talk about coordination number in a minute, but it's important that each of these cubic, you can imagine you're going to have like each atom arranged in this kind of three-dimensional arrangement. And if you put a square or a cube in the middle of them directly, you'll have exactly 1/8 of an atom in each corner, right? So you'll have 8 corners in a let's say a sphere. Wow. 8 corners in a cube, 1, 2, 3, 4 on the top, 1, 2, 3, 4 on the bottom. So then it would be 8 times 1/8, which means that in this first type of lattice structure called the simple cubic, there is 1 atom in the simple cubic and 1 unit of it. Does that make sense? That's very important to know. If they say simple cubic, I want to hear 1 atom. Okay. Then the coordination number. So coordination number is kind of difficult to understand. So if you picture, it's tough to picture, another one of these, let's say this atom that I'm hovering over is the middle. And you put another one of these 4 atom structures, one on top, one on the left, one on the right, one this way, one back, and one down in every direction. And you kind of made this the center. Then it would be touching 6 different atoms. So right now it's touching 1, 2, 3, 4, or really, I mean, it's kind of touching that. It's not really touching that one. So 1, 2, 3. If you had it going on again, you'd have 4, then 5, then 6. Or 4, then 5, then 1 from the top, which is 6. So they talk about it. Here's a video. I'm going to pull it over. They have a good graphic representation of it. So we can listen. Here, I'll mute it, but we can just watch. So here, imagine this one right here as the center. And then you're going to stack more of the cubics, the simple cubics on each side. And so right now, if you look at the green, you have 1 on the bottom, so that's 1, and then you have 4 touching on each side. So that's 1, 2, 3, 4, 5. When you put the next layer on the top, what's going to happen? You'll have the 6th one. The 6th one will be touching it. And if you look at it in that arrangement, hold on, let me get rid of the Yep, right there. You have a coordination number of 6. So 1, 2, 3, 4, 5, 6. Does that make sense? Okay, I hope it does. All right, so right now, simple cubic. It's the simplest one. It has 1/8 of the atoms on each corner. Its coordination number is 6, and it has 1 atom per unit cell. So this means if it has 1 atom per unit cell, and each corner is 1/8, and it's kind of arranged like this, that means each length, or the length of each side is going to be 2 times the radius of the atom. Because half of this cube would then be the radius of the atom. So 2 times the radius of the atom would give you the length. If you were to figure out the volume of this, think about what would you do? You would do 2 times the radius of the cube squared to figure out the square, and then multiplied by 3, or to the third. Because you would multiply it by 2 to get the area, then multiply it by, or not multiply by 3, then multiply it by 2, and then multiply it by another 1 to get the depth. So length times width times height is basically what I'm getting at, but I want you to see it in a more practical sense instead of memorizing formulas. Does that make sense? Yes? Okay. Good. So that's one. The second one is the body-centered cubic. So the body-centered cubic is a little more complicated. And it has the same phenomenon as the simple cubic, where you have 1/8 of the atom on each corner, but you also have body-centered. That's why we call it body-centered. You have one of the atomic bodies is in the middle of the arrangement. This gives us different numbers. Our coordination number is now 8, meaning if you were to stack multiple of these in every direction, each atom would be coordinated physically touching 8 different atoms. And we can see that here for the central one. You'll have 1, 2, 3, 4, 5, 6, 7, and then one behind, which is 8. If you stack another one on top, the 2 yellows won't be touching each other. But the yellows and the purples will be touching each other. So the coordination number is 8. And that means the number of atoms, you have the same 1/8 times 8, because you have the purple 8ths. So it would be 1/8 times 8, which is 1 plus 1 in the middle, which would be 1, and that would be equal to 2. So we have our atoms per unit cell for the body-centered cubic is 2, while the coordination number is 8. Are there any questions on that?
Professor, I don't have a question on that, but I'm here.
Okay.
I'm a little late though. Sorry.
Okay. So to figure out the length of the cubic, the body-centered cubic, is a little bit more difficult because we don't have something simple like we did for the simple cubic. That's why it's called simple cubic, where we can just multiply the radius by 2 to get the length. Now we have to do a little bit more work, and luckily they have formulas for us. So here's the formula for that. And I don't think it will be given, so it's good to know it, and the homework gives you good practice on it. And the length, so this would be the length would be 4r over the square root of 3. And the way they got that is trigonometry. So if you notice in here, you can actually calculate this L value when you know the diagonal of the diagonal, which is the diagonal here going from one corner to the other is going to be 1 radius, 2 radius, 3 radius, 4 radius. That's where they get the 4r from. And divided by the square root of 3, which would be this side. So that would be the math there. It's been a while for trig, but I don't know, SOHCAHTOA, whatever, all that stuff. Hypotenuse, whatever. So good luck with your trigonometry. But basically, for the body-centered cubic, you have 4r over square root of 3 equals the length of each side. You can cube this to give you the entire volume. Any questions on that? No? The next and last one is the face-centered cubic. So the face-centered cubic is the most complicated, and it has half an atom on each of the atomic faces, or each of the unit cell faces, unit faces. And you can see how that works in a 3-dimensional cross-section right here. And what this means is that for each atom, the coordination number is 12. So if you were to stack more, or if you were to look let's say, at this atom right here. The number of atoms touching it would be 1, 2, 3, 4, 5, 6, 7, 8. Then if we add another one of these next to it in the front, it would have 4 more touching, which make a total of 12. So that's what these coordination numbers mean. Coordination numbers are important for biochemistry and a lot of different things like, I'm sure you've heard of like heme, for like hemoglobin. So that's where the iron coordinates with the heme group. It coordinates in 4 different directions. There's certain different ions that can coordinate in proteins and things like that. And this is where the coordination number comes from. So it's how many can it bind, how many things can it possibly bind to? Or how many atoms can it be in contact with at the same time? So with the face-centered cubic, which again is the most complicated one because it has a coordination number of 12, and atoms, we didn't even talk about the atoms. There's 4 atoms in each of the face-centered cubics. And then the reason why is because we can have our simple cubic arrangement, which has 1/8 of the atoms in each corner. So that'd be 1/8 times 8, which is 1, plus 1/2 of an atom on each face, still inside the cube. And that'd be 6 of them. So it'd be 1 on each face, which is 6 faces, times 1/2, which is 3. So 3 plus the 1 from the corners equals a total of 4. So those are key things to know. And there is a summary chart, which I'll take a look at. And then we can calculate the edge. Based on trigonometry, we can calculate the edge of each of these face-centered unit cells. And that is 2r times the square root of 2. And we can use this in equation. So here we go. So calculate the density of aluminum. If it crystallizes in a face-centered cubic and has a radius of 143 picometers. Now, if you're given that the radius of the face-centered cubic is 143, what do we know? So we can go back to face-centered cubic and see, all right, the length is that. What is the question asking for? It's asking for density. How do we measure density? Grams per milliliter. Now, how I'm looking at your comment for slide number 12, are C and B equal? They are not equal because this is a diagonal across a 2-dimensional plane. This is a diagonal across a 3-dimensional plane. So it goes like super diagonal across from one corner of the cube to the opposite corner. So it's a little bit longer than B. But we know a squared plus b squared equals c squared. So that's how they understand. That's how they got this. I think they use trig. It's been a while. Okay, so going back to this one. Now the density is in grams per cubic centimeter or grams per milliliter. Same thing. Now we need to figure out the volume. We can figure that volume out in picometers or whatever unit we want, but we can convert it to picometer or to centimeters. Okay. So how do we do this? Well, I'll talk about it. So we know the radius. So we know. Well, I'll write some stuff down too. Let me get my pen out. I'll be lazy. I'm sorry. Pen is out. Hey, what does that? Okay. Okay. So we know our equation for the length of each of the sides of the face-centered cubic is 2r times the square root of 2. Okay, now that we know that, we can put in r. So we can put in r directly, or we can convert it to centimeters first. Doesn't matter. So it would be 2 times 143 times the square root of 2, which would be our length. And whatever we get for there, we can take that picometers and then convert it into centimeters. So picometers into centimeters. Let's just do it while we're at it. All right, so I got my phone, so we could do some math. 2 times 143 times the square root of 2. So times square root of 2. That equals 404.5 picometers. That makes sense. All right, so now we want to convert this picometers into centimeters. Now we know that, so what do we know? We can do a big conversion. So 404.5 picometers, when we know that 1 meter is 10 to the 12 picometers. 10 to the 9th is nano, 10 to the 12 is pico, times 100 centimeters divided is 1 meter. So we can do this math. Picometers cancel out, meters cancel out, and then centimeters prevail. So that would be, you're basically dividing it by 10 to the 10th. So divided by 10 to the 10th. And you end up with 4.05 times 10 to the negative 8 meters, or centimeters, sorry. Okay, does that make sense? I know, Adi, good job. Okay, so that's the first step. We have the centimeters. Now we need the volume of the cube. So what do we do with centimeters, which is, this is the length of one side? We can cube it. So we take that answer and we cube it. That can't be right. I think I missed a parenthesis. Hold on. 4.05 times 10 to negative 8. Divided by not divided by to the third. Oh, I was right. Okay. So you have, this makes sense actually. You have 6.64 times 10 to the negative 23rd. You get that. And this would be the volume. So this is going to be in centimeters cubed. Because we're cubing such a small number. Okay, now with the centimeters cubed, we now have this. We need the grams. So here's a little bit of thinking outside of the box. How would we find the grams? Any ideas? Molar mass. Yeah, so how do we use the molar mass? Don't be afraid to talk. It's okay. Yes, number of atoms. Good. Okay, so good enough. All right. So we can use the number of atoms in the face-centered cubic. So that's why we need to know how many atoms there are. And there tends to be, well, not tends, there is 4. So if we know there's 4, what we can simply do is just find the mass of an atom of aluminum. That's easy. We can just do 26.98 divided by Avogadro's number. This is grams per mole. We can figure out grams per atom. That would be some very small number. And then you can multiply it by 4. So times 4, which would give us the mass. Take this mass, divide it by the milliliters or the centimeters cubed, and then we get our answer. Yes, and fiddle it with Avogadro's number. I like that. Okay, so here's the math. We do 4 atoms of aluminum. 1 mole of aluminum is 6.022 10 to the 23rd atoms. And each mole weighs 26.9. And you get this many grams. And then you end up with this many centimeters. So then you do centimeters cubed. This is going to be in denominator. This is going to be in the numerator. And you get the density of 2.71, which is the true density of aluminum. And this is why the density of aluminum is pretty heavy, because it has this very complicated, squished together, face-centered cubic. Any questions on that? No? All right. Okay, so then you do the stuff. Good. All right, so summary. So the 3 types, we have our simple cubic, our body-centered cubic, and our face-centered cubic. It's very important to know the number of atoms in each cell. 1, 2, or 8, No, that's not right. 1, 2, or 4. The relative length of the cube relative to the radius to determine the volume, and you can use that to determine density also, and to compute the density. Also, the coordination number is important too. So here's a good chart encapsulating that information. So you have simple cubic, body-centered, and face-centered. This is slide 20 if you want to go back to it. And then they have this packing efficiency, which means which one is utilizing the space the best to pack in the most atoms. And that's going to be obviously the face-centered cubic. Okay, so now let's switch gears a little bit. We'll talk about different types of solids. And this is more in brevity. We're actually almost done, oddly enough. So classifying different crystalline solids. There are different types of crystalline solids within their class. Now you have molecular solids. It's okay, Dwayne. So in molecular solids, which are solids whose composite units are molecules, duh. Then you have ionic solids, which, guess what? They're ions, yeah. And then you have atomic solids, whose are atoms. Wow, that's so new to us, right? Now we know how to do that. You could also have non-bonding atomic solids, which means they're held together by dispersion forces. Things like that would be carbon, straight carbon, or not like graphite or anything, like straight carbon powder, or like phosphorus powder, which is they're held together by like very weak interactions. Where are we at? So here. Then we have metallic atomic solids, which are held together by metallic bonds. And then you have network covalent atomic solids. They're just covalent bonds. That's where you have your diamond, your ice, which is like that. Well, no, ice is hydrogen bond. Sorry, ice is non-bonding. No, sorry, ice is molecular solid. But network covalent would be like silicon. That's a good example. Okay, so here's just a chart of different examples. So you have molecular solids, which have ice, ionic solids, which are like different types of salts, NaCl, MgSO4, things like magnesium carbonate, like Pepto-Bismol, and different, or Tums, that has some calcium carbonate in it. And then you have atomic solids, which are the non-bonding ones, like you have solid xenon, any of the noble gases that are solid, which don't have any electronegativity, they would be considered a non-bonding atomic solid. And then you have metallic, like just straight gold or straight silver, and then network, which is going to be like diamond, and graphite, and different things that have covalently bound atoms together, but if they're all the same, and it creates a solid. All right, so we kind of talked about this already. Molecular solids, they compose of molecules. Don't really worry about the properties of them too much. We understand this already. We kind of get that already. So here's just a thing about diamonds. So, and this should make sense. I mean, diamond is just carbons bound together in a very pressurized rate. It was made with a lot of pressure, but with a very fixed covalent bond arrangement. Now, for all of them, it makes sense that they're sp3 hybridized because you have 4 bonds, there's a sea of carbons. So they're going to want to bond to each other, and they bond in a way that gives them this special arrangement, which is what makes diamond. And that gives them a tetrahedral geometry. So properties of diamond, you have very, very high melting point, 3,800. And because it's the covalent bond network is insanely strong. This is why it's considered like the hardest thing, and it's very expensive. So it's very rigid due to the directionality of the covalent bonds, and very hard due to the covalent bonds. So everything is due to the covalent bonds, it being so strong. So it's not, so it's the best thermal conductor, but it's not good at electrical conduction. It's an insulator because it doesn't have free electrons to bounce around to make current out of. And it's very chemically non-reactive, which is good. And you have graphite, which is similar, but it has an sp2 arrangement, which makes it a little bit weaker. And it has like trigonal planar sheets that are stacked on one another. Excuse me. Okay, almost done. So Band theory. This goes into crazy physics. So basically, the orbitals. So if you want to take a look at, we learned about hybridization, we learned about orbitals. If you take a look at orbitals with respect to how these solids interact with each other, all these different atoms in the solid, then we have to look at the amount of electron bands and energy bands that are being shared between these different atoms, and they're all coming into contact with each other. So for large numbers of atoms, the ones that are, when we have them really close together, we consider all of their energy levels as the same. We call them an energy band because they're so individually small that it doesn't matter how we categorize their electron energy. You either have a valence band or a conduction band. So either the bonding electrons or bonding orbitals or non-bonding or anti-bonding orbitals. That's where hybridization comes back a little bit. But again, don't go crazy on this. Those are just some definitions. And then band gap, this means that when you have a difference between the valence electrons band and the conductive band, you're going to have a band gap. So basically, the band gap only occurs, if you remember back to molecular orbitals versus bonding versus antibonding, when you have all bonding, it makes the bond order higher. So your valence bands are higher. But if you have a lower number, then you can have more of a more lower bond order that leads to more of a conduction band. So then the difference in those is the band gap. And why is that important? Well, for conductors, we need to be able to tell which one is the best conductor of heat, electricity, things like that. And it's based on those different band gaps. Again, don't go crazy on it. And then there's different types of semiconductors. And honestly, I'm not an expert at semiconductors, but basically there's different types of them. There's N-type and there's P-type. N-type is just charged with electrons just to make sure that it has its semiconducting properties. And P-type kind of makes like holes, which electrons can then jump like around, because generally the P-type semiconductors are not that strong. They don't have that many electrons. So if you have them jump around, then they will start to react more. So in essence, that's about it. Are there any questions on